Hello all of you. So in the last lecture we started discussing the lattice model of solutions. We have discussed the assumptions in the model. So I will continue from the point where we left and discuss how can we derive the expression for the Helmholtz free energy density using the lattice model, and then using the ideas that we have discussed earlier, we will find out the expressions for the binodals, spinodals and critical point for the case of the lattice model. So where we have been so far is we assumed that we are having a lattice and the solute and solvent molecules cannot just be anywhere, they need to occupy positions on the lattice, which pretty much reduces the dimensionality of the problem as we have discussed last time. So we can have solvent molecules depending on the number of solvents, they will occupy so many sites or cells in the lattice, and the remaining positions will be occupied by the solute molecules. So X here is my solute and O here is the solvent. So clearly both of them are assumed to occupy the same volume that is equal to the lattice volume, that is Vc. We have Np solute and Ns solvent molecules, and therefore I can define the volume fraction as Np by Np plus Ns, because the volume occupied by both are assumed to be the same. And then where we have been so far is we define the expression of energy for a configuration I as the energy of polymer solvent contacts multiplied with number of such contacts, the energy of polymer contacts multiplied with the number of such contacts, and the energy of solvent contacts multiplied with the number of such contacts. And clearly we can have many configurations which refer here to the different positions of the solute and solvent molecules. The total number of molecules are fixed. You can say N tot is Np plus Ns, and since the volumes are the same, the total volume is simply N tot multiplied by Vc. So now if I have to define the partition function for this ensemble, we can assume that the volume is constant, which is indeed the case here. So we are working with the canonical partition function. Which is given as sum over all the configuration exponential of minus EI by kBt. Now the key point here is we are not looking at the momenta of the molecules, and therefore we are only looking at the configurational part of the system, and that will basically contain only the information regarding the positions, not the momenta. Nonetheless, we can define the partition function for this system as Q here, but then if I also had to include the momentum contribution to that, if you think about it, I can write that as something like summation of I exponential of minus Hamiltonian divided by kBt, and that will now contain a kinetic energy part in addition to the EI here. Now, that kinetic energy part, if we think about it, that is going to be a function of momentums only, right. So, therefore, what this amounts to is saying that we have a configurational part that we are discussing here, and there is some other part, let me give it the name I, which refers to the momentum part of that, right. The reason why I can factorize this partition function into these two contributions is because the kinetic part does not depend on the position, right. So, we are only dealing with this part of the thing, and it turns out that the first part can be analytically evaluated under certain assumptions. I will not really get into that, but for this particular lattice model, that is inconsequential because the positions are fixed, as we had discussed earlier. So, nonetheless, now assuming that we are still working with the configurational partition function and everything else that we have derived still holds true, we may have some correction because of momenta, but not within the context of the lattice model. We can define the Helmholtz free energy as minus kBt ln of q, or minus kBt ln of summation over I exponential of minus EI by kBt. We can evaluate that by enumerating over all the possible configurations, and once we have that, we can find the Helmholtz free energy density as the ratio of Helmholtz free energy with the volume, or Helmholtz free energy per unit volume, right. So, this is where we are after, but it turns out that even that is of course simpler than doing it for a continuous system, but even then the possibilities are not very small. We have to think of all the possible arrangements of the molecules, and if you think about it, the number of arrangements here can be thought of the number of ways in which I can arrange n p molecules or particles on the lattice, because once I have chosen the position of the solute molecules, then the position of the solvent molecules are automatically fixed. That is true when we assume that each site is occupied by either a solute or a solvent molecule. So, we do not have any empty sites there. That again comes down to the idea of incompressibility. We are assuming both to have the same volume, and the overall density of the system is constant, and therefore, there are no empty sites present on the lattice. So, within that particular assumption, the number of ways in which I can arrange NP molecules is given as something like NP plus NS factorial, this is total number of positions, and picking NP sites for the solute, and of course, we will have NS for the solvent, which is same as NP plus NS combinatorial Cp. So, W we can evaluate, but for each of these W conformations, the EI are going to be different, right. They will depend on the values of the number of contacts in that configuration, and of course, the epsilon values we have assumed to be constant. So, the number of contacts however is going to vary. So, we will make use of what is known as a mean field approximation to further simplify the problem. And the assumption says that I will assume that all these energies in different configuration can be approximated by its average value. And since then I can find the average value, I can basically simplify my partition function. So, my Q would then be summation over exponential of minus EI by kBt, but since I have assumed every energy EI to be equal to E bar, this is pretty much W exponential minus E bar by kBt. And how do we evaluate this E bar is the following. So, basically the question that I am trying to ask, let us say if I look at any particular site on the lattice and let us say if it is occupied by the solute molecules, then what is on an average the number of solute contacts around it? What is on an average the number of solvent contacts around it? And what is on an average solvent contacts, but for solute molecules that is not counted, of course. For a solvent molecule we can count those contacts as well. Essentially we are interested in E bar as epsilon pp average n pp, that is the average number of pp contacts, plus epsilon ps average number of ps contacts, plus epsilon ss average number of solvent contact. So, for a solute contact you can see that there are in total z neighbors, where z is the coordination number. So, in total we have z neighbors per site, and what is the probability that any of these neighbors is occupied by a solute molecule. So, probability that a neighbor is solute, that is not very difficult to evaluate. That probability is essentially equal to the probability of any site being occupied by the solute molecules, and that is given by the number of solute divided by the total number of molecules in the system, right. So, as NP increases, we of course have higher probability that a site is occupied by the solute molecules, and when NP is equal to the N tot, that is there is no solvent molecules, clearly the probability goes to 1 because all the sites are occupied by the solute molecules. So, now if I multiply this probability with the probability of having a solute in the first place, we get the probability of the solute contact happening there. What we can also do is we can look at each of the solute molecules, in total there are NP of them, and find the number of contacts as NP multiplied with the probability that we had there. Multiplied with Z. So, Z are the total number of neighbors every solute molecules have, and each of them can be a solute with a probability of NP by NP plus NS. So, the total number of the solute contacts can be estimated to be this. Now, when we are doing that, we are going over every solute molecules and multiplying with the probability that the neighbor is a solute. So, clearly we will double count the contacts in this way, because every contact will have two solute molecules. Since I am counting over all the solute molecules, we will basically be counting every contact twice. So, therefore, we will divide this quantity by 2. So, what we essentially have is half Z NP, and this quantity is phi as we had discussed, half ZNP phi. Similarly, we can go ahead and find the number of solvent-solvent contacts. So, in total we have NS solvent molecules. Probability that a neighbor is solvent is NS by NP plus NS, and this has to be multiplied with Z, and this has to be divided by 2 again for the double counting. So, this gives me half Z NS multiplied with 1 minus phi. Finally, I can go ahead and find the number of solute solvent contacts. That is, again, first I locate how many solute molecules that we have, that is NP. The probability that the neighbor is solvent is NS by NP plus NS multiplied with Z. And now I am looping over all the solute molecules, but I am counting the solute solvent contacts. So, in this case we will not be having the double counting problem. So, this will appear simply like NP Z 1 minus phi. So, now since NP itself is equal to N tot multiplied with phi and NS itself is equal to N tot multiplied with 1 minus phi, if I put that thing in here, what we find is the average number of the solute-solute contact is equal to half Z N tot multiplied with phi square. The average number of solvent-solvent contact similarly is half Z N tot 1 minus phi square, and average number of solute-solvent contact is Z N tot phi multiplied with 1 minus phi. So, using this we can then find the expression of the average energy as epsilon Pp multiplied with half Z N tot phi square plus epsilon Ps multiplied with Z N tot phi 1 minus phi plus epsilon Ss multiplied with again 1 by 2 Z N tot 1 minus phi square. So, with this now I can take the Z N tot by 2 common from there, and I can estimate my average energy as Z N tot by 2 multiplied with epsilon Pp phi square plus epsilon Ss 1 minus phi square plus twice of epsilon Ps phi multiplied with 1 minus phi. Now, I can collect the terms containing different powers of phi here. So, what we have is epsilon Pp plus epsilon Ss minus 2 epsilon Ps multiplied with phi square minus 2 epsilon Ss phi plus epsilon Ss, and in the last term we have plus 2 epsilon Ps phi. For what we will discuss, it turns out that these linear terms are of no consequence in discussing the mixing and phase separation behavior. I will not derive it, but you can do the derivation keeping the linear terms, and you will figure out that these terms are not of consequence for what we are discussing. So, we only look at the quadratic term right here, and this particular quantity is what I referred as something like delta epsilon, that's in some sense characterizes the effective interaction. So, we therefore have E bar as Z n tot by 2 delta epsilon multiplied with phi square. So, before we proceed, let us say I want to focus on this effective interaction part and try to argue why we need to have this kind of a term representing the effective interaction here. So, the idea goes like this. So, the delta epsilon essentially characterizes the effective energy of a solute contact. And the reason why it is true is, let us say for example, I am looking at a small part of the lattice where we have some solvent molecules and 2 solute molecules, and in this particular configuration there is no solute contact. Now, let us say if I want to find the energy change when this solute swaps its position with the adjacent solvent molecules, so that the 2 solute molecules come together. So, the new configuration then would be so we have formed a new solute contact, but while doing that something else also happened. The number of the solute solvent contacts and the number of solvent contacts also changed while doing that, right. So, we clearly formed one new solute contact, and since that has an energy of epsilon pp, so we get that energy there. Now, let us look at what is the change in the number of solute solvent contacts. So, in this case, this guy was earlier forming 4 contacts with the solvent molecules, and this guy too was forming 4 contacts with the solvent molecules. So, in total we had 8 solute solvent contacts. In the new configuration, this guy is forming 3 contacts with solvent molecules, and this guy is also forming 3 contacts. So, in total now we have only 6 solute solvent contacts. So, therefore, we have 2 less solute solvent contacts. And that will result in an energy change of minus 2 epsilon Ps. Now, let us look at the solvent contacts. So, for many of the solvent molecules there is pretty much no change, only for some there is a change. Let us say if I start with this guy right here. So, it was having 2 contacts earlier, still it is forming 2 contacts in the new configuration. There is no change for this guy as well. But if I look at this guy, earlier it was forming a contact with a solvent molecule, but now it is forming a contact with a solute molecule. So, in this case there is a change by, so this guy underwent a change of -1, that is the decrease in the number of the solvent contacts. This guy was earlier having a contact with a solute molecule and now it is not having it. So, this guy will be basically be forming a new solvent-solvent contact. Earlier it was not present, it was forming contact with the solute molecule. All the other contacts remain as it is. So, both of these basically cancel. The same is true for these two guys. This guy have found a new solvent-solvent contact. So, there is a +1 here as a solvent molecule has moved in, and this guy is not affected. If I look at this particular guy in there, so earlier it was forming 2 contacts, but now it is forming 3 contacts there, but this contact we have already counted, right. So, we have actually 1 extra solvent-solvent contact that has been formed. Similarly, I can go over others. Basically, there is no effective change in this guy, this guy, this guy, and so on. So, we have 1 new solvent-solvent contact or pair. Okay, only 1 new pair has formed, and that will give me an energy of epsilon SS. So, in total, when the 2 solute molecules came together, the energy change is epsilon PP plus epsilon SS minus 2 epsilon PS, right. So, it is not only the solute-solute interaction that determines whether the solutes will come together, but it is also the solute-solvent and solvent-solvent interaction that dictates this particular process. Let us take an example. Let us imagine that my epsilon PP and epsilon PS is equal to 0. Now, in this particular case, what are we going to have? In this case, delta epsilon is simply epsilon SS. So, even though there is no energy change because of the solute itself, because solute, the interaction energy of solute with solvent or other solute is 0, but since the solvent-solvent contacts are changing, there is an energy change when 2 solutes come together. And when this energy change is negative, then we can say that the solute-solute contact is favored. On the other hand, if this energy change is positive, then it is clearly not favored. And this pretty much is responsible for, in the case of liquid water, the hydrophilic and hydrophobic behavior. So, basically it does not really matter, or it is not only important that we look at the solute-solute interactions alone. Even if the solute and solute interactions are favored, what is also important, and actually what is more important, is what is the solvent-solvent interaction and what is the solute-solvent interactions, and it is that dictates the solubility of the solute in any particular media. So, let us say for example, if 2 solute molecules want to come together, that coming together will be dictated by in which solvent I am doing the experiment on, and the role of solvent actually happens to be much more important in any cases, particularly when we are working in the dilute concentrations, because we simply have more solvent-solvent interactions present in the system as opposed to solute-solute interactions. So, that is the thing that we have to keep in mind, but let us get back to our partition function and see how far we have gotten so far. So, I have said that my Q is W exponential minus E bar by kBt within the mean field approximation and I can find the Helmholtz free energy as minus kBt ln of q, which will now be minus kBt ln of w plus E bar. Now, if I compare this with the expression of the Helmholtz free energy, F is equal to U minus Ts. So, U here is the same as the E bar. So, essentially this quantity has to be Ts and therefore, S has to be Kb ln W, which is of course true as we have discussed earlier in this course. So, now since W is equal to Np plus Ns factorial divided by Np factorial Ns factorial, ln of W is ln of Np plus Ns factorial minus ln of Np factorial minus ln of Ns factorial. Again we use the Stirling approximation. So, this becomes Np plus Ns ln Np plus Ns minus Np plus Ns minus Np ln Np plus Ns minus Ns ln Ns plus, by the way there is an Np here, plus Ns. So, again there are cancellations and what we can find is my S is equal to Kb multiplied with Np plus Ns ln of Np plus Ns minus Np ln Np minus Ns ln Ns. So, this I can now expand. This is going to be Np ln Np plus Ns plus Ns ln Np plus Ns. Now, we can collect the first and the third term and we will have Kb multiplied with minus Np ln Np by Np plus Ns minus, if I collect the second and fourth term, we will have Ns ln Ns by Np plus Ns. Now, this quantity is equal to my phi. This quantity is equal to 1 minus phi. This quantity is n tot multiplied with phi. This quantity is n tot multiplied with 1 minus phi. So, we can write this as Kb multiplied with n tot minus phi ln phi minus 1 minus phi ln 1 minus phi. So, if I put this expression of S back in the expression of F that we had there, what we will have is F is equal to E bar minus Ts. E bar we had already evaluated. This was half Z n tot delta epsilon multiplied with phi square, and now what we have is plus kbt multiplied with phi ln phi plus 1 minus phi ln 1 minus phi. which I can write as KBT multiplied with, by the way, there is also an n tot here. So, this gives me n tot multiplied with KBT bracket phi ln phi plus 1 minus phi ln 1 minus phi plus half z delta epsilon by KBT phi square. And this, if I divide by the volume, gives me the Helmholtz free energy density. So, F is F by V. Now, V also I can write as n tot multiplied by Vc, because Vc is the volume of both solute and solvent molecules. So, this will give me KBT by Vc multiplied with phi ln phi plus 1 minus phi ln 1 minus phi. This entire quantity I am going to give a name. I will call this minus of chi, and so this will be equal to minus chi phi square. So, the chi that I define is what I call the solvent quality, that is equal to minus 1 by 2 z delta epsilon by KBT. So, basically we have been able to evaluate the expression of F for the lattice model. Now, once we have that, now we can go ahead and find the phase behavior by basically using the apparatus that we have discussed earlier. We can find the second derivative and determine whether we have a tendency of mixing or for phase separation, and then we can also find the expression of binodals, spinodals and critical point, and that we will take it in the next lecture. So, with that I want to conclude here. Thank you.